In this video, we will review some of the key terms for this section and then give some examples of how some of these concepts can be used to solve chemical problems. In most chemical reactions that contain more than one reactant, one of the two reactants, when you're mixing them together, is going to run out before the other. The limiting reactant is the reactant that is completely consumed in a chemical reaction and limits the amount of product that can be formed. The other reactant would be in excess. There would be some left over when you're all done with the reaction. The reactant in excess is any reactant that occurs in a quantity greater than what is required to completely react with the limiting reactant. This means that the excess reactant will be left over when the reaction goes to completion. The theoretical yield is the amount of product that can be made in a chemical reaction based on the amount of limiting reactant. The actual yield is the amount of product actually produced by a chemical reaction. So the actual yield is what you actually get. The theoretical yield is what, in theory, given the amount of limiting reagent you start with, the maximum amount of product that you should be able to get. The percent yield is a way of guiding how close you got to the theoretical yield. The percent yield is calculated as the actual yield divided by the theoretical yield times 100 to convert it into percent. This would give you the percent yield. Let's now look at a couple problems that have to do with the concepts of limiting reagent, theoretical yield, actual yield, and percent yield. So first, ammonia, NH3, can be synthesized by the reaction 2 nitrogen monoxide plus 5 hydrogen goes to yield 2 ammonia, NH3s, plus 2 waters. If we start with 86.3 grams of NO and 25.6 grams of hydrogen, we want to find the theoretical yield of ammonia in grams. So essentially we are starting out with amounts of each one of our reactants. Currently we don't know which one is going to run out first, but one of them will. So the way we want to approach this problem is determine how much both the amount of NO, nitrogen monoxide, and H2, how much each one of our starting materials could produce in ammonia. Whichever one produces less, that is the one that will run out first. And the value associated with that in terms of the amount of NH3 that is produced will be our theoretical yield. So starting with NO, our value for NO, we have 86.3 grams of NO. In the end, we want to know the number of grams of ammonia that this could produce. So our end answer that we want is grams of NH3. We have information about one substance and we want to determine information about another. So what we'll need is in the middle to use a mole to mole ratio. But before we can use the mole to mole ratio, we need to convert our starting point into moles. So we will take this and multiply it by molecular weight with grams on bottom and moles on top. So moles of NO, grams of NO. 1 mole weighs the molecular weight of NO. So we now need to determine the molecular weight of NO. The molecular weight of NO would be equal to 14.007, the molecular weight of nitrogen, plus 15.999, which is the molecular weight of oxygen. This gives us a total value of 30.006 grams per mole. So our value on the bottom here would be 30.006. Our grams cancel out, and so we're now in moles of NO. We can now convert from talking about nitrogen monoxide to ammonia by using our mole to mole ratio. So we'll put moles of NO on bottom so that it will cancel out, and moles of ammonia, NH3, on top. From our chemical equation, 2 moles of NO yields 2 moles of NH3. So we put a 2 and a 2. We can cancel out our moles of NO. And now, if we were to stop, we would have the number of moles of ammonia that could be formed. But we want to find the grams. So we will take this value and multiply it again by our molecular weight, this time with the grams on top and the moles on bottom. Now we want the molecular weight of NH3. So the molecular weight of NH3 would be equal to the molecular weight of nitrogen, 14.007, plus 3 times the molecular weight of hydrogen, 1.0079. If you plug this into your calculator, you will find that the value is 17.0307. And this is grams of NH3, moles of NH3, and then a 1 there. Our moles of ammonia will cancel out, and this will now give us grams of NH3. So if we plug this into our calculator, we will get a final value of 48.9819 grams. In terms of significant figures, our first value has 3, the next value has more than 3, a mole-to-mole ratio doesn't come into play, and our last molecular weight, our last value, has also more than 3. So we will cut this at 3 significant figures because everything we're doing is multiplication. Okay, so this is the maximum amount of ammonia that we could possibly get from the amount of nitrogen monoxide that we're starting with. Now let's calculate the amount of ammonia that we could get from the hydrogen that we're starting with. So for the hydrogen, we're starting with 25.6 grams of hydrogen. Again, we want to find the grams of ammonia. We will again multiply by our molecular weight using the grams on bottom, moles on top. 1 mole, this is molecular weight of hydrogen, the diatomic hydrogen. So that would be 2 times the weight of a hydrogen atom, which is 1.0079. This gives us 2.0158 grams per mole. So we would put 2.0158 grams on the bottom, and H2, those cancel out. We now have this in moles. We can now multiply by our mole ratio to convert from moles of hydrogen to moles of ammonia. We'll put moles of ammonia on top, and we'll put moles of hydrogen on the bottom. Going from our balanced chemical equation, 5 moles of hydrogen yield 2 moles of ammonia, and so we'll put the 5 on the bottom, which goes with the hydrogen, and the 2 on top that goes with the ammonia. Our moles of hydrogen now cancel out. So if we were to do the calculation up till this point, we would have moles of ammonia, but we want grams, so we're going to keep going. We then multiply this by our molecular weight, grams on top, moles on bottom, and this is moles of NH3, grams of NH3. 1 mole is, we already worked this out before, the molecular weight of ammonia is 17.0307. Our moles of ammonia cancel out, giving us grams. Plugging this into your calculator, you will get 86.514 grams of ammonia. In terms of significant figures, our first value has 3, the next value has more than 3. Our mole-to-mole ratio doesn't come into play, and then our last value has more than 3 significant figures. So our end answer will have 3 significant figures. So our end answer would be, we would find the one that produces less. The one that produces less in this case is the NO, the nitrogen monoxide. It produces only 48.9819 grams of ammonia. The hydrogen, we have enough to produce 86 grams. So our limiting reagent would be the NO. Our theoretical yield would be 49.0 when we round our value up, and this would be grams of ammonia. One thing to be aware of is, although the mass of the NO was more than that of hydrogen, it ended up being the limiting reagent. So just by looking at the masses, you won't necessarily be able to tell which one of your components will be the limiting reagent. You need to do the calculation. Let's do another problem. We can obtain titanium metal from its oxide according to the following balanced equation. TiO2 as a solid plus 2 carbons also as a solid yield 1 titanium as a solid plus 2 carbon monoxides. When 28.6 kilograms of carbon reacts with 88.2 kilograms of titanium 4 oxide, 42.8 grams of titanium is produced. Find the limiting reactant theoretical yield in kilograms and percent yield. So we have 2 different starting materials, so one of them is going to run out first. We just need to determine which one that is. So let's calculate the amount of titanium that each can produce, and then we can figure out our percent yield based on the amount of titanium that was actually produced. So first, let's look at carbon. So from carbon, we're starting with 28.6 kilograms, and in the end, we want to produce kilograms of titanium as a metal. So we're starting with information about one thing. This is kilograms of carbon, and we're ending with information about another. So somewhere in the middle, we're going to be using a mole-to-mole ratio. In order to do that, we need to convert into moles. So we'll have to first convert out of kilograms into grams, then use the molecular weight to convert into moles, and then we can use our mole-to-mole ratio. So let's convert this into grams. 1,000 grams is equal to 1 kilogram. That will cancel that out, and we'd be left with grams of carbon. We can then multiply this by our molecular weight with moles on top, grams on bottom. 1 mole is 12.011 grams. Our grams cancel out, and we'd be left with moles of carbon. We can then multiply this by our mole ratio. From our balanced chemical equation, 2 moles of carbon give us 1 mole of our titanium. So moles of carbon go on bottom, mole of titanium go on top. 1 mole of titanium is 2 moles of carbon. Our moles of carbon cancel out. Up till this point, we would calculate the number of moles of titanium. We can then multiply this by our molecular weight with moles on bottom, grams on top, and this will give us the grams of titanium produced. 1 mole weighs 47.867 grams. Our moles will cancel out. We'll now have grams of titanium. We wanted kilograms, so we'll need to multiply this by 1 kilogram is 1,000 grams. Plugging all that into your calculator, you'll end up with 56.99 kilograms. Figuring out our significant figures, our starting point has 3. This conversion is a definition, so it doesn't come into play. This value has more than 3. This is a mole-to-mole ratio, so it doesn't come into play. This value here has more than 3 sig figs. And the last value is a definition, and so it also doesn't come into play. The least of these was our starting one, which had 3, and so our end answer will have 3 significant figures. Next, we need to calculate the amount of titanium we could get from the titanium oxide that we're starting with. So our titanium oxide, our titanium 4 oxide, we're starting out with 88.2 kilograms of it. We need to convert this into grams. 1,000 grams per 1 kilogram. This is of titanium. Kilograms cancel out. Titanium oxide. Times, we need to convert it into moles. So we're going to put moles on top, grams on bottom. And then the molecular weight of our titanium 4 oxide would be 52.8626 grams. Our grams cancel out. This gives us moles of titanium 4 oxide. We can then multiply this by our mole-to-mole ratio, which is a 1-to-1 ratio. So moles of titanium 4 oxide. 1 mole of titanium comes from 1 mole of titanium 4 oxide. We can then multiply this by our molecular weight, 47.867 grams per 1 mole of titanium. Our moles of titanium 4 oxide and moles of titanium cancel out. We want it in kilograms, so we now need to multiply this by 1 kilogram is 1,000 grams. So the maximum amount of titanium that we could get from our titanium oxide would be equal to 52.8626 kilograms of titanium. If we compare our two numbers, we'll see that this second value is less than the first. In terms of significant figures, this one will also have 3 sig figs. Because this value is less, that means that our titanium 4 oxide is our limiting reagent. That also means that this amount here would be our theoretical yield. Which would be equal, in terms of correct sig figs, 52.9 kilograms of titanium. Our percent yield would be equal to our actual divided by our theoretical times 100 to convert it into a percent. So this would be equal to our actual amount was 42.8 kilograms. What we could have produced, given the amount of titanium 4 oxide that we started with, was 52.8 kilograms. Multiply that ratio by 100 to convert it into percent, and we end up with 80.965 in terms of significant figures. Cuts between the 9 and the 6, and this is percent. So this would give, as an answer, 81.0%, and that would be our percent yield. We will finish up our discussion of chemical reactions with a category of reaction that is particularly important: the combustion reactions. A combustion reaction involves the reaction of a substance, one of those that contains carbons and typically hydrogen, with oxygen to form one or more oxygen-containing compounds. If the substance has hydrogen, then generally you're going to form some water. And in a combustion reaction, you get energy that comes off in the form of heat. So an example of combustion reactions would be the combustion of methane. We take methane that is commonly in the form of gas, reacting it with 2 oxygen molecules, and this will produce carbon dioxide as a gas and water as a liquid, as well as some heat. The key component here is that for a combustion reaction, you would have your fuel plus oxygen in the gas form, giving you typically carbon dioxide as a gas plus water as a liquid and heat. The actual component here is going to change, but the other 4 components are going to remain relatively the same, though you will have different coefficients in front for your balanced chemical equations.